Hi, I'm Nicholas Rouse. Before I get started, I want to thank the organizers of this nearly carbon-neutral geometric topology conference in general, and the organizers Tam and Khan of the number theory and low-dimensional topology topic group in particular. I am also contractually obligated to tell you that my postdoc is partially funded by the Pacific Institute for the Mathematical Sciences, or PIMS, which is a research institute and consortium of universities on the west coast of North America. One thing that PIMS focuses on is acknowledgement of the peoples who lived on the land that our universities now occupy. So in that spirit, I would like to tell you that the Vancouver campus of the University of British Columbia, which is where I work and live, sits on the traditional territory of the Musqueam people. Okay, for the math today, I would like to tell you about ramification of hyperbolic knots and what that means, which is a core component of my thesis work. To keep the talk to 30 minutes, I will mostly focus on the bigger picture and avoid delving into details of any proofs that I wrote in grad school. Since this is a public YouTube video, I won't actually say any of my email addresses, but if you happen to be able to find one of mine on your own, please do feel free to email me about anything in this talk, even if you come across it after the conference. Okay, now I'd like to collect some background information and running hypotheses, so in case I forget to say anything, I told you at the start. The manifolds in this talk will be orientable and compact, with either empty boundary or boundary disjoint union of tori. This is where finite volume hyperbolic 3 manifolds live, and they're going to be our primary object of study. Work of several people, Thurston, Perlman, Mostel, Prasad, and a whole bunch of other people, establishes this great richness of hyperbolic manifolds in dimension 3. One can study the geometric structures that can be put on 3 manifolds, and it turns out that there are 8. One has to be a little bit careful about what one means about putting these geometric structures, but suffice to say there are 8 geometries. And by far, the most interesting one, at least to me, and probably the least well understood one, is the hyperbolic one. And moreover, these hyperbolic structures are rigid, meaning that if a manifold supports, if a 3 manifold supports a finite volume hyperbolic structure, then that structure is unique. So in particular, any geometric information that one gets from this hyperbolic structure is actually topological information. So for example, the hyperbolic volume of a hyperbolic 3 manifold is actually a topological invariant of the underlying topological space, or the underlying topological manifold, if you like. In this case, we will realize hyperbolic orbifolds as quotients of PSL2C, which is isomorphic to the orientation-preserving isometry group of hyperbolic 3 space, by discrete groups, which we will call Kleinian groups. Don't worry too much about this orbifold rather than manifold for right now. It's just a mild generalization of a manifold that's more natural in this quotient by discrete group situation. The main arithmetic invariants of a Kleinian group are its trace field and quaternion algebra. Actually, there are slightly more refined invariants that are better behaved in some sense, but for this talk we'll focus on the more naively defined ones. Suffice to say that for knots at least, the naive and refined invariants agree. Okay, the trace of an element of PSL2C is well defined, modulo signs, and we can consider the set of all traces of a Kleinian group and adjoin them to Q. Okay, so far nothing interesting. But the point is that what one gets out of this procedure is a finite extension of Q, of the rational numbers. And we call such a field a number field, by the way. Said another way, all of these traces are algebraic, and for any given Kleinian group, finitely many of them suffice to obtain all the others from addition and multiplication with themselves and with rational numbers. And we call this field the trace field. Perhaps a less familiar kind of object is this A naught gamma you see there on the slide, which is the trace field span of all of the elements of gamma, and we give it a multiplicative structure just coming from the group. It turns out that this object is what's called a quaternion algebra, and then in the next slide I'll tell you more about these objects. Okay, here's some algebra for you now. We're going to stay away from characteristic 2. Everything can be made to work, but what I'm going to give you is not a correct definition in characteristic 2. Given 2 non-zero elements of a field, which I'm calling little k here, we can form the 4-dimensional k vector space with basis traditionally called 1, ij, and ij, with multiplication defined by I squared equals a, j squared equals b, and I and j anti-commute. So in particular, thanks to our assumption on the characteristic, this is always a non-commutative algebra. And we call this object we get a quaternion algebra. And we package it all together in this Hilbert symbol, which I've written here. Let me caution you that this is not always what people mean when they say Hilbert symbol, but it's what I mean in this talk. And it is a nice notation in the sense that it emphasizes both the elements and the field, since as we'll see, the underlying field is quite important. Okay, probably the standard thing that mathematicians think of when they hear quaternions or quaternion algebra is what I'll call the Hamilton quaternions in this talk, which in our Hilbert symbol notation will be -1 over the real numbers. And so the good news for Kleinian groups is that under mild assumptions on the elements you choose, you can fairly easily write down a Hilbert symbol in terms of traces of those elements. In particular, I've written at the bottom here, but the first entry is the trace squared of g minus 4, and the second is the trace of the commutator of g and h. And like I said, there are some sort of mild assumptions on g and h, but for the most part, it's fairly easy to write down. I'm going to give you some basic properties for manipulating Hilbert symbols. There are many more identities, but these are perhaps the most important. The first is the most important, which is that every quaternion algebra is either isomorphic to the 2x2 matrix algebra over the base field, or it is a division algebra, which means that every non-zero element is invertible. Implicit in this is also the fact that the 2x2 matrices over a field are always a quaternion algebra. Often we say the algebra is trivial or split if it is a matrix algebra, and we say it is division or ramified if it is not. Saying that the algebra is ramified is a slight abuse of language, and we'll come to a better contextualized notion of ramification later, once we start changing the base field. The second is that only the square class of the Hilbert symbol entries matters, and this fact is expressed in the isomorphism of quaternion algebras given by Hilbert symbols, where we remove x squared and y squared. The last one I want to mention is that if either Hilbert symbol entry is a perfect square, then the algebra is trivial. The way I've written it here has 1 as the first entry, but using the second bullet point, one can put any perfect square there. From this, we can immediately see that the Hamilton quaternions are the only division quaternion algebra over the real numbers, because there are only 2 square classes in the reals, represented by 1 and -1. So the only way to get something that could be non-trivial is if both entries are -1, and this is exactly the Hamilton quaternions. Okay, let's try to bring it back to some topology for a bit. If you're watching a talk on number theory and hyperbolic 3 manifolds, there's a decent chance you have some affection for the figure 8 knot complement. Abusing notation slightly and writing elements of PSL2C using their lifts in SL2C, we can generate the fundamental group by these 2 elements here. From these, it's hopefully clear that adjoining a third root of unity, which I've written as zeta 3, suffices to generate the trace field. Moreover, from these matrices, we can see that the quaternion algebra is trivial. Indeed, one can take the first matrix here and subtract off the identity matrix to get something that is not invertible. So our fundamental dichotomy, or if you like, just some matrix algebra, tells us that the algebra is trivial. This applies to all cusp hyperbolic manifolds by more or less the same argument. Fundamental groups of cusp manifolds have these parabolic elements, from which one can obtain a non-invertible element of the quaternion algebra. Okay, so one might think that the quaternion algebra is not an interesting object for cusp manifolds, since it carries exactly as much information as the trace field. Let me just say at this point that for closed manifolds, one does often have non-trivial quaternion algebras. And as a big picture goal for this talk, I would like to try to convince you that there is an interesting quaternionic object, even for cusp manifolds. It just takes a lot more work to set up. Speaking of closed manifolds or orbifolds, here's how we usually obtain them from cusp ones. The picture here on the left is the exterior of the figure 8 knot, which I've written E of k, together with some decoration. I've drawn this blue torus neighborhood around the knot, which remember we deleted from the 3-sphere. The meridian and longitude on this torus are the red M and green L, respectively. The operation of hyperbolic Dane surgery glues in a solid torus, which I've written as V, and drawn in blue to the right of the figure 8. We glue in such a way that the boundary of V is identified with the torus in the exterior of the knot, and moreover such that the meridian mu of the solid torus is identified with m to the p, l to the q, where p and q are integers. This will add a single relation to the orbifold fundamental group, namely trivializing m to the p and m to the p times l to the q. We get a manifold whenever p and q are coprime. Moreover, even allowing p and q to not be coprime is the theorem of Thurston that all but finitely many choices of p and q will give you a hyperbolic orbifold if the thing you started with is itself hyperbolic. Okay, that's a lot of topological details, but the thing to keep in mind is just that there is a way to produce lots of closed hyperbolic orbifolds from a cusp one like a knot complement. Let's try to bring the algebra and the topology together. Consider the 9-1 Dane surgery on the figure 8 knot. You can take my word for it that this manifold is hyperbolic and that its trace field is generated by a root of this degree 7 polynomial that I've written here. This polynomial has 3 distinct roots, so the trace field has 3 distinct embeddings into the real numbers. Calling one of them sigma, we write a naught gamma to the sigma for the quaternion algebra over the reals obtained by embedding the Hilbert symbol entries into the reals via sigma. If you like, you can also view this as taking the tensor product of the quaternion algebras over the number field with the real numbers, where the real numbers are given the structure of an algebra over the trace field coming from this embedding sigma. I've chosen this example so that any choice of the 3 embeddings gives the Hamilton quaternions, but in general, one could have some embeddings giving a division algebra and some giving a matrix algebra. This embedding that makes the algebra the Hamilton quaternions is enough to conclude that the original quaternion algebra over the trace field is a division algebra itself, because the matrix algebra remains the matrix algebra after changing the field. As promised, this is the more refined usage of ramification. In particular, we say that a naught gamma is ramified at these embeddings into the reals. It turns out that the embeddings into the reals are only part of the story. The other part of ramification is embeddings into the p-adic numbers. If you don't know what they are, that's okay. All I will say for now is that they're obtained by a metric completion of the rational numbers, just like the reals, except the metric is better attuned to the arithmetic of the rational numbers. The p-adic fields and finite extensions thereof, together with the real and complex numbers, are known as the local fields, at least in characteristic 0. The global fields in this talk are number fields. There is some information on this slide, but the thing to take away is that quaternion algebras over global fields are completely determined in terms of their embeddings into local fields, where it is easier to figure out what's going on. In particular, local fields other than the complex numbers have a unique quaternion division algebra, and the complex numbers only have the 2 by 2 matrices. So to understand a quaternion algebra over a global field, which, let me remind you, that quaternion algebras over global fields are exactly the objects associated to hyperbolic 3 manifolds, one should study their embeddings into local fields. More specifically, one should study the ramification at the local fields, which completely determine the global field algebra up to isomorphism. In particular, there is a finite set of ramified embeddings, and this set is finite of even cardinality. It is a complete invariant of the global field quaternion algebra. Let's go back to this surgery on the exterior of the figure 8 knot, and look at the embeddings into the p-adic numbers. There is an embedding into the 2-adic numbers that makes the quaternion algebra division. Moreover, this is all of the ramification for the quaternion algebra, 3 real embeddings and 1 into the 2 adics. At this point, I'll pose what I've called question 1, but there is no question 2 in this talk. The problem is, given a knot, what are the primes p, for which there is a hyperbolic Dane surgery on the knot, such that the quaternion algebra for the surgeon manifold has a ramified embedding into a finite extension of qp. This is somewhat technical phrasing, but the broader thing to keep in mind is just how does the ramification behave as one varies the surgeries. Depending on the context, one can think about coarser versions of this question. For example, just whether the set of such primes is finite or infinite. For the figure 8 knot, Chinberg, Reed, Stover tell us that we can only have ramification into finite extensions of Q2 and into the reals. In contrast, my thesis work tells you that for the knot called 7-4 in Rolfson's tables, and for an infinite family of twist knots, the corresponding set is infinite. The goal for the remainder of the talk is to try to explain what's going on as best as we currently understand it. As a preview, let me say that it's related to this cooking up of a non-trivial quaternionic object for cusp manifolds that one can specialize to obtain the quaternion algebras for the surgeries. I will try to make this more precise, but for now, hopefully it's believable, because this question is tied up in how quaternion algebras change as one looks at various hyperbolic Dehn surgeries. Okay, here are some theorems that, at least on their face, provide some explanation, but now the Alexander polynomial is appearing seemingly out of nowhere. I won't spend too much time on this slide just reading the theorems, especially since the YouTube videos can be paused. I do want to say that my thesis work is about making progress on this conjecture about when the sets of primes are finite or infinite. Eventually, we're going to need to connect the quaternion algebras back to this Alexander polynomial condition, but for now, let me at least give you a precise statement of my work. Here are the core theorems of my PhD thesis. Again, I won't spend too much time on this slide since I mentioned the results before, and one can pause to read if need be. To study how the quaternion algebras vary through surgeries, we need a base space, so to speak, where all the surgeries live. The space we will use is called the canonical component of the SL2C character variety. I won't get into too much gory detail, but let me say that it is an algebraic variety that has the discrete and faithful representation, which gives the hyperbolic structure, for the fundamental group of a knot complement as a point. Moreover, all the hyperbolic Dehn surgeries are points on this algebraic variety as well. It is a theorem of Thurston that the dimension of the canonical component as an algebraic variety is equal to the number of ends of the manifold. So for knots, there is only one end, so the canonical component is a curve. More generally, for an n-component link, the canonical component will have dimension n. It's called the character variety because the points are really characters of representations into SL2C. But in this context, that is enough to determine the geometrically interesting representations up to equivalence. I'm ignoring any subtleties with lifting from PSL2C in this talk. I will point out that there are other representations on this variety. In particular, there are reducible representations, and moreover, there are non-abelian reducible representations, which are the key to this condition star on the Alexander polynomial. Let's do the figure 8 knot as an example of a canonical component. The answer is going to depend on your choice of presentations and coordinates, but using the one shown in this slide, we get a variety determined by the vanishing of this two-variable polynomial in R and T written here. Let me say that different choices of presentations or trace coordinates or what have you will give you isomorphic algebraic varieties. Also, we now get our first fancy quaternion object. The first pass is defining a quaternion algebra over the function field of the curve. If you're not familiar, you can think of the function field as the field of fractions of the polynomial ring Q adjoin R and T modulo the relation giving the canonical component. The entries also deserve some mention. They're the regular functions, which I've written I here, which associate to an element of the group the character at a particular point. Now we come to the most fancy generalization of quaternion algebra in this talk, an Azumaya algebra, specifically a quaternion Azumaya algebra. Recall that this mathcal A here is the function field quaternion algebra defined on the previous slide. The naive question which I've written here is just whether one can specialize the function field algebra at any point on the canonical component and get a quaternion algebra over a suitably chosen field. The correct way to ask this question is to ask whether there is an Azumaya algebra over the canonical component that the function field algebra extends to. I won't tell you exactly what an Azumaya algebra is, but let me give you a somewhat fraught analogy. Asking whether these function field algebras extend to an Azumaya algebra is superficially similar to asking whether a meromorphic function extends to a holomorphic one. Instead of dividing by 0 or something like that, in the complex analysis case, we have to worry about whether the entries of our Hilbert symbol specialize to 0. But in complex analysis, just because it looks like you might be dividing by 0 with your equations doesn't mean that the singularity isn't removable. And similarly, in our case, just because it looks like you might specialize to 0 doesn't mean that there isn't an Azumaya algebra that the function field algebra extends to. At least for simple poles in complex analysis, the thing that tells you whether you have a removable singularity is called the residue. Similarly, for Azumaya algebras, the function field algebra extends over a point if and only if there's a trivial residue at that point. Of course, let me caution you that these two residues have wildly different definitions, so don't focus too much on the language. I will say that this condition star is really about the residues, and I'll attempt to explore this further in the last few slides. Before doing that, though, let me say that if the function field algebra extends to an Azumaya algebra, then through some now classical work in algebraic geometry, you know that there are only finitely many primes p for which there is a hyperbolic Dane surgery, such that the quaternion algebra associated to that Dane surgery is ramified at an embedding into a finite extension of qp for that prime p. In fact, one gets control over all the points, not just the Dane surgery points. My work, of course, then has to be in the context where the algebra does not extend. Work of Harari will tell you that the corresponding set is infinite, but without guaranteeing that you can find the infinitely many primes among the Dane surgery points. So my thesis work is really about proving that the infinitely many primes can be found even when restricting attention to the Dane surgery points. As I mentioned before, this condition star on the Alexander polynomial is really about the non-abelian reducible representations on the canonical component. And it has to be, because the function field algebra always extends over all the irreducible representations. The point is that the trace field of these reducible representations looks like Q adjoin W plus W inverse, where W is a square root of the Alexander polynomial. I say trace field, but really it's the residue field in the sense of algebraic geometry. Unfortunately, this residue field is yet another usage of residue, distinct from the ones mentioned before. I call it the trace field in scare quotes here because at the points where the trace field makes sense, like those corresponding to hyperbolic 3 orbifolds, the trace field is the residue field. This calculation of the residue field really goes back to de Rham and is about what one can arrange the traces of meridians to look like at the reducible representations. In this last slide, I want to tell you how to calculate the residues and where Q adjoin W comes into the picture. The point is that the residue can be regarded as a field extension. Usually one will see the residue defined in terms of some Galois cohomology group, but the element of that cohomology can be identified with a quadratic or trivial extension in this case. Moreover, in this case, the base field is Q adjoin W plus W inverse, and the extension is Q adjoin W. So if Q adjoin W equals Q adjoin W plus W inverse, then the extension and hence the residue are trivial, and the algebra extends. If you made it this far, I want to thank you for watching, and I hope I was able to tie together the various strands about quaternion algebras, ramification, Azumaya algebras, residues, canonical components, Alexander polynomials, reducible representations, and probably some other things I'm forgetting by now. As part of the conference, I will have office hours at 9 a.m. Eastern on Saturday, September 24th. So if there's anything you want to ask about, please feel free to show up there, or again, send me an email. Okay, thank you again for watching.